I don't know why I can't. I don't know why I cannot.
Don't worry, priorities first. I can wait.
Okay. So let me. So I'm gonna admit everybody in the waiting room now.
So sorry, Angel, you're gonna have to do that yourself. I don't know why I can't do that. And Julia as well, actually.
No problem. Yeah, I'll do in a second. So, I mean, first of all, welcome everybody to VSET seminars. We are very happy to have you with us today. Today, we have Eduardo Perez-Richet from Science Pop, who's going to talk about fraud-proof non-market allocation mechanisms. It's a joint work with Vasiliki Skreta, who's also with us. And we have as guest panelists, Julien, Combe, and James Schummer. So thank you all for joining us today. Just as a reminder, next week we have another seminar, same time, same day, Thursday. In this occasion, we're going to have Weiji Sloan from Stanford, who's going to talk about martingale embeddings, theory and applications. So thanks again, Eduardo, for joining us today. The floor is yours.
Well, thanks a lot for the invitation. I'm very happy to give this online seminar. So let me start by commenting a bit on the title. So fraud-proof non-market allocation mechanism. So it's an allocation mechanism. We're going to be allocating objects, say social housing, for example, or it could be prizes. Right? It's going to be non-market in the sense that transfers are not going to be allowed in the mechanisms. And we're going to require the mechanisms to be fraud-proof. What does it mean? Is since transfers are unavailable, allocation is going to be based on the characteristics of the agent. And the agents will have the possibility of falsifying these characteristics. All right. So we're going to require the mechanism to. We're going to require that the mechanism does not give the agents any incentive to actually falsify or commit fraud, right? And this is not going to be without loss of generality in terms of the optimality of the mechanism for the designer, because we are in a setup where the revelation principle doesn't apply, right? So I'll clarify that, and I'll try to justify why we are interested in this fraud-proof mechanism, since they are not optimal in this setup. All right, so let me start right away with the model. So the problem is to allocate a mass row of homogeneous objects or prizes, say if you want to have something concrete in mind, think social housing, to a unit mass of heterogeneous agents, and we're doing so without transfers. All right. The agents, each of them is going to be characterized by a type vector that is independently drawn from a joint distribution. And this type vector is multidimensional, so let me explicit all the dimensions that are of it. All right. So I is going to be a group identity, and it's going to be basically a way for us to put together all the characteristics of the agent that are both observable and not falsifiable. Okay, so it could be race, gender, or any other things of this kind. All right. Then the most important part of this type is going to be the score of the agent, which is going to capture the characteristic that the allocation is going to be based on. Say, for example, for social housing, that could be your percentile of income. Okay. So we're going to assume that it's a one-dimensional characteristic that is distributed on a support that may depend on your other observable characteristics, right? And this score is going to be observable by everyone but it is possible that the agent has falsified it. So what the principal and other people observe is the possibly falsified score. All right. Other aspects are the valuation, how much the agent values getting the object, the gaming ability, which is going to be a scalar of the cost of fraud for the agent, and the social value of giving the object to this particular agent for the principal. All right. The valuation, the gaming ability are all private information to the agent, and the social value could either be private to the agent or unknown to both. All right, and the outside option of not giving the object to any agent is normalized to 0. Okay, then let me.
Eduardo,
Yes?
could I hate to interrupt so early. Could I go back and ask a clarifying question on the model? Actually two. The first, the gaming ability, should I interpret a higher gamma as being that it's easier to manipulate, or a higher cost? Which the direction?
The gaming ability is the lower cost.
So a higher ability is lower is a lower gamma? Or
No,
is
the higher gaming ability is a higher gamma, which is a lower cost.
okay, so it is ability. Okay, and social value. What is the social value of what? I didn't quite understand that one.
The social value for the principal of giving the good to the agent.
Okay, is that a function, not a function of their type?
That's going to come on the next slide. It's possibly random, but of course it's going to be positively correlated with the score, basically, which is why the allocation is based on the score.
Thank you.
Okay, so here it is actually everything that we need about the distribution. So each group has a certain size mu I, which they sum up to 1 since there's a mass 1 of agents. And we'll be interested in the score distribution conditional on the group that you belong to. Okay, and we're going to assume that it has a CDF. We denote by Fi. It's going to be atomless, and we'll have full support on Si, which is the possible support for members of this group. Okay. Then about the conditional value and gaming ability distribution, because we want the mechanism to be fraud-proof, the agents that are going to be most important in terms of the incentives constraints are the ones for which the stakes of the game are the highest. They are the ones that have the highest incentive to falsify. So these are the agents with the highest possible gaming ability and the highest possible value for the group. So what we're assuming about the distribution is that no matter what you can learn as the principal, which is the group I and the score S, you cannot exclude the possibility that agents are of the highest gaming ability and valuation possible. Okay, so it's always possible that you have the sort of the worst types of agents in terms of preventing them from falsifying. The conditional social value is positively correlated with the score in the following sense that your expectation of the social value W given the group of the agent and his score is increasing in the score. Okay, and we write it as a function Wi of X. All right, and finally, it will also be important to know what's the average social value in a certain group. Okay, so that's Wi bar. All right, so the payoff of the agents is going to be given by the probability that they get the object multiplied by their value for the good minus 1 over gamma. So here, gaming ability. Indeed, a cost function of falsifying that is possibly dependent on the group, and that is a function of your true score, the source score, and your the score, the falsified score. T is for target. Okay, and we're going to make at this point only basic assumptions about the cost function, but there are stronger assumptions that are going to come later. All right, the basic assumptions are that not falsifying has 0 cost, and that the cost is strictly increasing in the distance between the target and the source. All right. We're also making some kind of regularity assumption. So let me make it simple here. let's assume that it's just continuously differentiable for the purpose of the talk. We make the assumptions a bit weaker because it turns out that only upward falsification, trying to pretend that your your score is higher than it really is, it's the only kind of falsification that's going to matter, but let's say continuously differentiable. And we're also assuming that the cost of falsifying to T if your true score is S is always dominated by a constant times the distance between T and S. Okay, so this regularity assumption. All right. Now, to anticipate a bit on what we're going to be doing, we're going to be solving the problem under different assumptions on the cost function. And really, what I want to say at this stage is there's no real notion of what this falsification cost should look like. So we want to be flexible in the assumptions. This is to justify our approach of doing it under different kinds of possible assumptions. All right. So as I said, the mechanism is going to be non-market in the sense that transfers are not going to be available. So the only thing that the principal can do is to commit to an allocation rule based on the group of the agent that he observes, the score that he also observed but may have been falsified, and some possible reports that the agents could be making about the other dimensions of their type. All right. But actually, it will never be possible without transfer for the principal to obtain any information about these other dimensions of the type. If different agents would report differently, I mean, if you allocated the good differently for different reports, you would always get the agents to make the report most favorable to them. All right. So let's take the simple approach right away and say that. For us, a mechanism is just going to be an allocation rule, which is a group-specific probability of giving the good to the agent given the score that you observe. Okay, so we're framing it as a mechanism design paper, but actually, if instead the principle was designing an information structure so as to inform a decision maker about the score, there would be no difference in the problem, right? As long as the decision maker is aligned with the principle. Okay, so I gave the examples of social housing. You can think also about emissions testing for vehicles. Vehicles are allowed to go on the market if they are below a certain level of emissions. The giving green labels or other kinds of labels based on again pollution. Or for another example, we show that shows actually the existence of falsification. There's this small example that in France they have this special tax regime, which is which involves a simplified declaration for firms that are sufficiently small. I think it's below 20 employees, and they have this paper where they show that actually, obviously, the number of firms that are just below 20 employees, that declare to be just below 20 employees, is actually much bigger than it should be. That there's an accumulation there, and they actually discuss in this paper the fact that it's not that the incentives, that the firms manage to keep the number of employees lower than 20, is actually that they misdeclare the number of employees to benefit from the simplified tax regime.
Eduardo, maybe I have a conceptual question on this. So in practice, maybe it's not easy to distinguish for the policymaker what is I in your model and what is the score. So usually it's not easy to know in which dimension can you lie and you have a cost, and in which dimension you are publicly available. So I think about university admission, for instance, there are plenty of criteria they want to prioritize. And then it's so I know it's very outside of the model. I was just thinking, what would be your thinking? So probably help based on your intuition of mechanism design, probably you would start to observe bunching on some dimensions if people can manipulate. So that would be the type of things that you would you would recommend to a policymaker to check to know whether he can make an allocation depends on some dimensions or not?
I mean, possibly, yeah, you could be interested in showing that some dimension is actually is falsifiable and gets falsified. No, obviously, I mean, you know, in practice, it's likely that there's a lot of things that are possibly falsifiable at different costs, and we're really taking the approach that you know, some of them are either really too costly to falsify, and there's one that can be falsified. Yeah. So, but indeed, you would have to identify first what was the relevant.
So should I interpret your I as a score that has an infinite cost of falsifying, and so that would be something that I'm sure that the policymaker can base this allocation?
Yeah, I mean, of course, that's an interpretation that is just too costly to falsify. Yeah. And we took it to be just I didn't specify it. We took this group to be finite, infinite number for simplicity. So it's a discrete characteristic, but that's not hugely important.
Okay.
All right. Okay. So as I said, we're going to focus on fraud-proof or falsification-proof allocation rules. We actually know that these are not optimal. We know that because it's related to previous paper we wrote on the topic, which was information design. So as I said, in fact, it doesn't really make a difference in this setup. So we know that at least for some cost of falsification, the optimal mechanism must actually induce some fraud. All right. So the fact that we're going to be imposing falsification proofness is going to be costly for the principal. So why are we taking this approach? So we think that actually it might be a desirable property to satisfy for the mechanism designer for, say, political or stability reasons. You often, I mean, allocation procedures that induce fraud often get attacked on the basis of this. Actually, you see a lot of this kind of attacks of different kinds of social rights or social housing in France from typically extreme right politicians. So the fact that when you create the allocation mechanism, you want to create something that is stable and that you're not going to have to change later on might imply that you want to be fraudulent. Okay. Another aspect is that the fact that people who, if you actually design the optimal mechanism which involves some fraud, the fact that there's going to be some fraud could have a negative social externality. It's a topic that has been touched in some empirical papers. For example, in Eisenman, they show that in Mexico, in states where there's higher levels of corruption, students cheat more in exams. So this kind of negative externality argument. All right. Another aspect is that when you're doing these mechanisms, which basically is about making the threshold of admission higher than your true threshold, and expecting people between the true threshold and the one that you're setting to commit fraud, to falsify, right? It implies some cost on the side of the agent that is not taken into account. And also, if there's heterogeneity in gaming ability, these mechanisms that rely on fraud may generate some kind of lack of fairness among the participants. Right? And finally, there's also a theoretical aspect that, in principle, if we can characterize both the optimal mechanisms and the optimal falsification-proof mechanism, it's going to be a way to have a formal measure of the cost of falsification-proof. All right, so these are the reasons why we are doing this. Now, let me get into the analysis. So we're going to impose falsification proofness as a constraint. And what it's going to say is that the difference in probability that you get from pretending that your score is T when your true score is S, the difference in probability that you get from like has to be actually lower than the cost of performing this falsification. all right, than the cost of performing this falsification for the agents that have the highest stakes in the game. Again, so for the agent that has the highest gaming ability possible and the highest possible value for the group. All right, so that's why I never wanted to exclude them for any possible score. All right, and since I'm going to put this together, let me call kappa I the product of gaming ability and value, and I'm going to refer it to the stakes in the rest of the group. So possibly if you're allocating objects instead of prizes, you might have a resource constraint as well. So you have a constraint, let's say that the mass of allocated objects, which is this object here, is less than the mass of available object, which is rho. We may accommodate some quotas. So a quota says, for example, that the share of objects, the share of total objects that you're actually allocating to group I has to be higher than a certain phi I. Okay, so we can have a quota system like that. And there's an implicit constraint that's going to play an important role, which is that obviously the mechanism is giving probabilities to give the good. So each alpha LS has to be between 0 and 1. All right, so that's the problem with the principle. All right, this is separating across group, that the mass of any group within a group you're summing over agents with different scores that has this distribution. For each score you're allocating with this probability, and that's how much the principal values allocating the good to someone in group I with score S, and you're doing that subject to all the constraints. All right.
So Eduardo, so I understand that even without quotas, this is already interesting, and that will be the core of your analysis. But I was wondering, so in matching, typically, the way we see quotas will be that we have in mind that there are some objectives behind that the policymakers would like to implement, and the quotas are just the implementation of this objective that we hope would arise endogenously, but we never had, I would say, or a few papers have tried, but we never had a good mechanism design justification of quotas. And I was wondering, would there be a possibility to make the quotas arrive endogenously from the objectives here, rather than putting them as the constraints? What would be your thoughts on this?
I haven't thought about that. Typically, I think when say if you're designing a social, I mean, we may be interested in some objectives. Why are quotas optimal? But typically, when you're designing some policies, they are often going to come as a constraint from the outside. So sorry, I'm not really answering your question, but I'm more defending the point of view that in certain design problems they should come rather as constraint than as objectives.
No, I definitely agree. I'm just saying, there is this gap in the literature that somehow it would be nice to make these quotas arise endogenously from some objectives. So some paper in matching with constraints, like Fuito and co-authors, have tried to push toward this direction of what can be done. And since you are taking a mechanism design approach, I was wondering whether you have thought about this in this framework. And I think the framework you are proposing can be also a natural framework to make this happen. But,
no, we haven't really talked about that, but thanks for the comments. All right. Theoretically speaking, quotas and resource constraints are going to very soon disappear. So let me actually do this bit of magic, and we're going to go back to a problem that is as if we had only one group and there was no resource constraint and no quota constraint. And that's just done by putting some Lagrange multipliers both on the resource constraint and all the quota constraints. It turns out that if you do that, so if you write the Lagrangian, you just get a similar objective function with a slightly modified social value function for the principal. Okay, it's just basically it's going to be about changing the outside option of not giving the good to the agent. All right. So that's what it's going to look like. Basically, you're going to have a different, instead of the outside option being 0, no, you want to allocate when the social value is higher than a certain threshold WI hat for a group, and this system of thresholds, group-specific threshold, just comes from the Lagrange multiplier, right? So the procedure is no, we're going to solve the problem with a given system of thresholds, and then you adjust the thresholds to satisfy the constraints. All right. It turns out that once you've written the problem in this way, you've got rid of the resource and the quota constraints. Now the problem is entirely separable, so you can solve the problem group by group. Okay, so we're going to focus on how to solve the problem within a group given a certain threshold within this group. So now we have only one group, and we have modified the value of the principal to take into account these thresholds. All right. All right, and I'm going to refer to this quantity here. So at a given score, the social value minus the threshold that possibly comes from quota and resource constraints multiplied by the mass of agents with score S. I'm going to refer to this as the social surplus at a given score. All right. Okay, so that's the problem we're dealing with. Just some intuition, which is not going to be very surprising, but if you didn't have the falsification proofness constraint, so basically, agents could not falsify at all. What you would like to do is just give the good to any score that's higher than the threshold W hat, since the function W of S is increasing. That's giving the good to all agents that are above a certain score threshold that I'm going to call S hat. So that would be the optimal allocation rule. Now the problem if you do that is that you create very strong incentives to falsify for those agents that are just below the threshold. All right. And actually any discontinuity would do that. So what you want to do is to increase the probability of giving the good somewhere around the threshold and smoothly enough so that you don't create any incentives to falsify. So we expect the optimal allocation rule to look something like that. And what's important to understand how it behaves is, what is the interval over which it grows, and what shape does it have? So we're going to show that the size and the shape of the growth interval is actually going to be pinned on by three principles. Of course, the probability constraint is going to matter. You cannot exceed probabilities violate the bounds of a probability. So that's going to matter to determine the length of the interval. But the important principle, what characterizes what can be a growth interval, is going to be a principle of zero average social surplus. The possible growth intervals are going to be intervals such that the average social surplus conditional on the scores being drawn from that interval will have to be zero. Okay. Within this interval, what's going to determine which one of them? So these are always intervals around S hat, obviously, which is to the right of them. Social surplus is positive, to the left of S hat, social surplus is negative. So to get a zero average social surplus, you have to be on both sides. And what's going to govern the size is the probability constraint. You cannot increase the interval so much, otherwise probabilities would go to higher than 1 or lower than 0. And that's also going to be a principle of extreme score error avoidance. All right, so you will want to avoid making errors of allocation for scores that are either extremely high or extremely low. And which side you worry about actually is going to depend on the average social value in the group. All right. And then once we do that, we'll be able to characterize the exact shape of the allocation rule, which is going to be pinned on by the incentive constraints. But of course, there are a lot of incentive constraints, and the issue is going to be which one of them are going to die, which one of them are going to actually matter for the shape. Okay, so first, intuition, as I said, allocation rule should be smooth enough, not only continuous actually. Any any smoothness of the cost function should be inherited in some form by the allocation rule, so as not to provide any incentives to falsify. Okay, so I'm gonna, given the regularity assumption that I impose on the cost function, actually what we're gonna get is that the optimal allocation rules, or actually any allocation rule that satisfies the falsification proofness constraint, will have to be Lipschitz continuous. All right.
So Eduardo, maybe can you go back one slide, please? So about your, okay, so the growth, so if I'm trying to think about the link between the primitives and then the design itself, if I want to have a more prior-free approach, so the interval will be determined by the distribution of types. So this, if you are unsure about the distribution of types, that would be mostly the interval that will be affected, if I'm not mistaken. And then if you know more the technology of C, then that will be the shape once you have defined an interval that will be affected. Am I right in saying this? If I want to see that, assume that the designer knows well the C but does not know well the F and wants to be a bit more robust to the F, am I right to say that then your technique can still be used to have the growth in, region, but not maybe the interval would change a bit in between the win?
Yeah, so okay, the general shape of the growth interval only depends on the distribution, but where it stops, which one you're choosing actually depends also on the cost function.
Okay, I see.
All right, so, and then the shape, the final shape obviously completely depends on the cost function, and much less so on the distribution actually.
Okay, I see. Okay, great. Thanks for that.
All right. So Lipschitz continuity is going to be useful because we're going to be able to write the actual usual integral decomposition that we write for that we use in mechanism design, except that we're not going to do it on the utility that the agent is getting, which is the usual trick. We're going to do it directly on the allocation rule. Okay, because it's Lipschitz continuous, we can write it as the allocation rule at the lowest score plus the integral of its derivatives, which exist almost everywhere. All right. And it's going to be useful to do it either from the leftmost point, the lowest possible score, or from the highest possible score. So that's why I wrote both forms of this integral decomposition here. Okay. The second point is that optimal allocation rules must be monotonic. Okay. So to show that, take any allocation rule like the one you have on the slide, and you can build an allocation rule that does better as follows. You're going to choose the highest increasing function that's everywhere below the allocation function that you started with to the left of S hat, and the lowest increasing function that's everywhere above to the right. Okay, so you get something like that. It's an increasing function. It's everywhere above your former allocation rule for scores that are above the threshold, so it's good for the principal, and it's everywhere below for scores that are below the threshold, which is also good for the principal. All right, so these rules must be monotonic. Okay, and now knowing all this, we're going to use this decomposition to figure out the growth interval, basically to write a differential version of the program using integration by part, and that's going to give us the growth interval. Right? And it works in this way. I'm going to write it slightly differently depending on what we call the priority of the group, whether it's low priority or high priority, and basically that's based on how the average social value in the group compares to the threshold social value. Okay, if the average is below, we're going to say that the group has low priority. If it's above, we're going to say that it has high priority. And which version of the integral decomposition we're going to use to write the differential program depends on which group we're dealing with. If we're dealing with low priority group, we're going to construct the test, the allocation rules from the left, from the lowest scores. And if we're dealing with high priority group, we're going to construct them from the right. Okay. So let's take the low priority group, for example. If we use integration by part in the objective, what we get is that the objective is equal to the allocation probability that you give to the lowest score multiplied by the difference between the average and the threshold, which, since we are in a low priority group here, is negative. Okay, so that tells us that basically we want to set the lowest allocation probability to 0 in the low priority groups. Okay, and then we integrate over the derivative of the allocation rule. Okay, and what we have here is like a cumulative surplus that corresponds to the surplus that you get by increasing the allocation probability at a certain score, which means that you're going to increase it at least by the same amount if we're dealing with monotonic allocation rules for all the scores that are above this probability. Okay, so and I'm going to explicit what these cumulative surplus functions are. All right. I've added in the program monotonicity as a constraint, which is without loss of generality, since we know that we can focus on monotonic allocation rules for optimality. All right, and I've just rewritten the probability constraint and the falsification proofness constraint in their differential form. All right. Now, actually, setting alpha lower bar to 0 only relaxes the constraint, which means that we know that in low priority group, we're going to give the good with probability 0 to the lowest score, and we can get rid of the alpha lower bar in the constraint. Okay. And in the high priority group, actually, instead what you'll have is the probability that you give the good to the highest possible score multiplied by the difference between the average and the threshold, which is no positive, and that's going to mean that we want to set the probability of getting the good to 1 for the highest scores. So you have this principle that I mentioned of avoidance of error for extreme scores, which is going to be playing for the highest scores in the high priority groups and the lowest scores in the low priority groups. And so let me go back to a differential form of the program that gets rid of these extremes that we've fixed and actually brings back together again the two kinds of groups, high priority and low priority. I'm going to do that by using a single version of the cumulative social surplus there, and then that's the differential program that I get. Okay. All right. So what is the objective here? Again, when you're raising the probability of giving the good at a certain score S, so your alpha prime S ds is just raising this probability. As I said, you're increasing the probability that all scores above are getting the good by the same amount. Okay. What is the value of that for the principal? How much social surplus does he get out of that? It's going to be. It's going to be the social surplus function. So it's the integral from S to the highest possible score of social surplus at all possible score. Okay, that's how much I add in value. All right. Now, that being the program, let me just put a Lagrange multiplier on the probability constraint and write the Lagrangian. And what I will get is that my new objective function is going to maximize the integral of alpha prime times the difference between the cumulative social surplus function minus the Lagrange multiplier. All right. And what it means is that you want to set alpha prime equal to 0, so the allocation rule to a constant, whenever this cumulative social surplus is below the Lagrange multiplier mu. All right, and that's what's going to pin down the growth interval, since it's going to be constant out of this set in this set. So that pins down where you want the allocation rule to increase. All right, and it turns out that no matter what the distribution and W functions are, these cumulative surplus functions that have a very specific shape, they are bell-shaped so they are single peak with a peak at the threshold itself. All right, and what is going to mean then for them to set alpha prime equal to 0, or the allocation rule to a constant, when this cumulative social surplus is below a certain value of the Lagrange multiplier means that you're going to be on an interval, between two scores that have the same cumulative surplus, which is actually equal to the Lagrange multiplier. All right. So that's where the intervals come from. You see that in low priority group, there's going to be some scores on the left where the cumulative surplus is going to be negative. So because the Lagrange multipliers are positive, that means no matter what the Lagrange multiplier is, you never allocate the good to this guy. Okay. Again, that's the error avoidance at the extreme that's kicking in, and that's limiting which kind of intervals you can choose. All right. And what does it mean for the cumulative surplus to be equal at the lower end of the interval and at the upper end of the interval? It actually means exactly what I said the other principle was. It means that if you're integrating social surplus between these two bonds, you actually get zero average social surplus between these two bonds. All right, so that's the other principle that's pinned on these growth intervals. All right. Okay. Another thing that gets defined in this picture, if you want, is give me the lower end of a possible growth interval. I can give you what's the associated upper end. Okay. So it's the point, the score to the right of the threshold that gives me the same cumulative surplus. Okay. And I'm going to use that to define a matching function that pairs lower ends of the intervals to higher ends of the interval. Okay, and this matching function is going to actually play an important role in the characterization. So what we show is not completely immediate from there, but basically we've determined the growth interval, and what we show as a result in the paper is that in fact it's sufficient for us to solve the problem that we had, but reduced to actually all possible growth intervals. So all possible intervals from S lower star to S upper star, where S lower star and S upper star are matched so that they form a growth interval. We're going to solve this problem reduced. No, we don't have the parts of the integral that are outside of this, reduced to this growth interval. Once we do that, we're going to basically select the growth intervals that makes either of the two following conditions bind. Either the difference of probability between the highest point of the growth interval, the lowest point of the interval is equal to 1. Okay, so if you go further, you'll be violating the probability constraint. Or maybe you never violate the probability constraint, but actually you get constrained by the fact that in the low priority group there are these guys to the left to which you never want to allocate the group. Okay, so when the probability constraint does not kick in, what's going to kick in is this avoidance of errors at the extreme. All right, and that's what's going to pin down the exact growth interval once we have solved for the reduced problem of all possible intervals. All right. So now we are left with this reduced program that we can actually write either in its differential form or in its original form. And now here's where I'm going to need more assumptions on the cost function, is to actually solve for the shape of the optimal allocation rule over this growth interval. All right, and I'm going to make two classes of assumptions. I'm going to solve the problem either for cost function that have either increasing differences or decreasing differences, okay, which is the usual meaning. So think of it, the cross derivative being positive. It's upward because it only matters for falsification targets that are above the falsification, the true score. Okay, because I restricted. And I showed it was necessary to restrict to monotonic allocation rules. This is the only kind of falsification that I have to be afraid of. Okay, so if you want to have an intuition of what these conditions capture, think of a cost function that would be a function capital C of the distance between T and X. Okay, we can call that Euclidean cost function. So if C is concave, then I'm going to satisfy the upward increasing difference. Okay, so what is a concave cost function? You can think of it as the technology of falsification having sort of increasing returns to the scale of falsification. Right. Upward decreasing differences, by contrast, going to be convex Euclidean cost functions, and it's going to capture something like decreasing return to scale to the scale of falsification. All right. So I'm going to provide solutions that are different under the two kind of assumptions. The most usual and simple one is going to be when the cost function is convex, the upward decreasing differences, then actually the incentive constraints are going to bind locally, and we will be able to rely on a first order approach. Time is passing, so I don't know if I'll actually do this, but I'm going to focus on the most interesting one, which is the upward increasing differences case, because in this case, it's not the local incentive constraints that bind, and so actually the way we solve it is through sort of new method based on an analogy with optimal transport. All right, so that's what I'm going to start with. Okay, so remember we're focusing on this reduced problem that only has basically the falsification proofness constraint left, and that is reduced to intervals that are of the gross intervals kind, so they have a zero average social surplus within the interval. Right? And what I did on this slide is that actually I just split the gross interval between scores that are below the threshold and scores that are above the threshold. Right? I split the objective function here. All right. The second thing that I'm going to do is that I'm going to relax the incentive constraint. I'm only going to keep the constraint that scores below the threshold should not have any incentive to falsify to scores that are above the threshold. All right. So here is this next slide. Yeah, I'm only looking at the incentive constraint between score S that are below and scores T that are above the threshold. And I wrote upward increasing differences here because, in a lot of what I'm going to do next, it's not going to be clear where the upward increasing differences assumption plays a role. But it's actually going to be important to recover the missing incentive constraints once I've found the solution. All right, now I've relaxed the problem, so I will need to recover the other incentive constraints and so on. So we shouldn't forget that it plays an important role. All right, so that's the next transformation. Let me further transform this program to make the analogy with optimal transport. All right, so I'm going to change the spaces over which these things are defined. So here I have the space of scores that are to the left of the threshold. Okay, these are scores that are between S lower star and S hat, and here I have the space of scores that are above the threshold from S hat to S upper star. Okay, and instead of identifying them by the scores, I'm going to identify them by their distance to the threshold. Okay, which I'm going to recall. I'm going to call Y for those scores that are to the left, and Z for those scores that are to the right. So let me rewrite these spaces. Now the same points are before at Y and at Z, and I have spaces that start at 0. The distance starts at 0. All right. And I'm going to put a probability distribution on each of these spaces. Okay. And basically, the probability distribution, you can think of the density of this probability distribution as being proportional to the amount of social surplus that lies at any point Y or at any corresponding score S. Okay, so the density, if you want, of, let's do it on positive here, the density of the mass density that's at a point Z is proportional to the social surplus that's created at this point. What is the social surplus created at this point? Well, it's the social value in excess of your threshold on social value multiplied by the mass of agents that actually lie there. All right, and I'm doing the same on the other space, except what I'm distributing now is negative social surplus. So on the left, I have a space of negative social surplus that are located at some scores, and on the right, I have a mass of positive social surplus that is again located at different possible scores. All right. And I'm also going to rewrite in different ways the probabilities that actually the allocation rule is allocating to these different locations, different scores. Right? So I'm going to rewrite phi y to be the probability that I'm giving to scores that are on the left of the threshold, the negative social value scores, and psi z the probability that I'm giving to positive social value score or positive social. All right. Now, here is the program that I get. My integral of alpha times these social values, it becomes an integral over space z over the probability that I'm giving to this scores, and I'm integrating given this probability distribution, which now is a distribution of positive social surplus. And negative social surplus on the other side, that's in the other set, it comes as negative value for the principal, okay? And that's the probability that I'm giving them, and that's their distribution. What's the incentive constraint now? It says that the probability at positive social value z minus probability at any negative social value score y is less than this curve, okay? And this looks like optimal transport in the following way. We can recognize it as the dual of the classical optimal transport problem, which is the following. The primal optimal transport problem that corresponds to this dual would be the problem of minimizing the transportation plan to the joint distribution that have marginal p on the negative social surplus space and q on the positive social surplus space, and that performs. So basically, you know, it transports all this mass that's on the negative side to the positive side, all right, in the least costly possible way. The reason that there's the same total mass is because we have these growth intervals that have this specific property that the average social surplus on the growth interval is actually zero. All right. And that's the second place where upward increasing differences plays a role. What upward increasing differences tells us is that the cost function here in the optimal transport problem is actually a submodular function. And we know how to solve this kind of optimal transport problems. We know that in this case, what you want to do is assortative transport. So basically, you're going to transport this negative social value, social surplus score here corresponding to y to the z, so that, well, actually here what we're going to recover in this assortativeness is the matching function that I defined that associated each possible beginning of a growth interval to each possible end. It's the same matching function. Because what does it say? It says basically that the amount of social surplus of negative social surplus that you have between 0 and y is equal to the amount of social surplus that you have between 0 and z. That's the condition for you to transport from y to z, and that's been done by the matching function. All right. If we go back to our initial problem, what it says is that the incentive constraints that are going to bind are between these points on the left-hand side of the threshold and this point of the right-hand side of the threshold that are matched. So that are possible ends for the growth interval. All right. Turns out we know formulas for the prices. Well, they are interpreted as prices usually, the optimal transport problem, but here for us they are probabilities. Up to a constant, and then we can adjust them to the probability. So that's going to pin down basically what the optimal allocation rule is going to be for us. I wrote it down on the slide. You can see that it depends on integrals of partial derivative of the cost function. And you can see also, because that was one of the questions you asked, Julien, where the distribution is playing a role here. It's playing a role in what are possible ends or beginning to these intervals. And it's also playing a role through the matching function that appears here in the definition of the allocation. All right. So I'm not going, I mean, it's close form, but it's still a bit complicated. And then once you have this is for any S lower star, S upper star, and then as I said, you adjust them to either satisfy saturate the probability constraint, or saturate the fact that you don't want to allocate, you don't want to make errors on allocation at the extremes, which extreme depends on which group you're dealing with. So that's what's captured here. Okay. So let me go quickly over the first order approach. Local incentive constraints are going to ban. Basically, what it's going to mean is that you're going to restrict you're going to how much you increase the test at any score S by how much you increase the allocation rule. So alpha prime of S is going to be bounded above to satisfy the first order condition, which means it's going to be bounded above by the derivative with respect to the target, to the falsification target locally at this point. And since between S lower star and S upper star, we're in this space where the social surplus is positive, that means you will want to maximize the derivative at this point. You will want to increase as fast as possible, which corresponds to the intuition, which means that basically you will want to set the derivative of the test equal to that value at this point. All right. So now we get shape of the test that depends on this marginal cost of falsification. Okay. Look. No, I don't have much time left. I don't know exactly when we started, but let me just mention some properties of the rules, and that actually apply to both upward increasing difference and upward decreasing difference cases. All right. So I've put low priority group and high priority. So what do we know? We know that in the low priority group, we want to make sure that there are some types at the left that are not getting the group. And what it can mean, because you want to pin down this allocation probability to 0 for these guys, it means that you may have to make errors on the other side if the stakes are very big for the agent. So the incentives to lie are very high. So if kappa is high, the fact that you want to keep preventing these agents from getting the good means that you may have to give it with probability less than 1 to agents at the top. The opposite is happening for high priority group. All right. Now we can do comparative statics over the stakes. If the stakes are very high, so that actually this constraint is playing that you're not giving the good with full probability to the top agent in the lowest group, then increasing the stakes is actually going to make the probability of getting the good worse for every agent. But if the stakes instead are low, so this constraint is not kicking, so you're actually going from 0 to 1 in terms of probability, then increasing the stakes is going to rotate the optimal allocation rule, and it's going to rotate it in the sense that it's making the allocation worse for high scores and better for low scores. Okay, so you can see, remember what are the stakes? This kappa is the highest gaming ability multiplied by the highest possible value for the good, and you can think of this comparative stats maybe of what's the externality imposed by the most skilled frauders in the group on other people in the group. So in the sense that if you were to eliminate this highest one or reduce the highest gaming ability in the group, how would it change things? And typically, if the extreme avoidance, the extreme error avoidance constraint is not binding, it's going to have a different effect on high scores and low scores. That's sort of what it's saying. In terms of the principle, we can say that the social surplus obtained by the principle is higher than just the threshold social surplus that he's targeting, and also that the payoff is actually decreasing in the stakes of falsification for the agent, which makes sense. Okay, I have a bunch of qualitative results, so stop me when I'm going over. I'm going to try to focus on the most interesting ones, but yeah, stop me when I'm done. All right, we can we can also say something about, since we have this thing about returns to scale, we can try to say something about that, and for that we have to focus on the class of Euclidean cost, and then you can define. If you normalize them so that the sort of the distance that you need to falsify in order to make it worth gain from probability 0 to probability 1 is the same across all cost functions. And then within this class of functions, you can interpret returns to scale as being a sort of convexity order over this Euclidean cost function that we have here. All right. And then what we're going to get is the same kind of effects. We're going to get rotations when you're increasing the returns to scale, and roughly speaking, higher returns to scale, so more concave cost functions, will have the same sort of effects as lowering the states. Oh yeah, and actually you can say more about the shape of these allocation rules when you're in this class of Euclidean cost functions. If you're on the upward decreasing difference side, so the convex Euclidean cost functions, then the optimal allocation rule is always going to be linear with slope C prime of 0. And if you're on the upward increasing difference side, so concave Euclidean cost functions, you can say that the allocation rule is going to be first convex below the threshold and then concave above the threshold. Okay. You can say something about the distribution, but it's not clear cut. So maybe let me go to more qualitative result that sort of should say something about also the choice of characterizing this optimal falsification proof allocation rules. So we can try to compare to what would have been the optimal allocation rule without this constraint. Turns out we know how to do that in certain cases. That's what we did in our former paper with Vasiliki. When do we know how to do this? We know how to do this when the gaining ability and value of the agent are homogeneous. So everyone is at the same gaining ability and value. And we are in the upward increasing difference kind of class of cost. Okay? And what does this comparison bring us in these cases where we know how to do it? Well, what we can say is that in all agents prefer the constrained optimal, the falsification proof optimal mechanism to the unconstrained optimal. Okay, so in a sense, obviously the unconstrained optimal is better for the principal, but worse for the agents, for all agents of any score, and the fraud-proof optimal allocation rule is a bit worse for the principal, but it's better for all the agents. Okay, and the point it allows us to make is that if you think that the principal should actually care about the cost of fraud, the cost of cheating for the agent, it's very hard to, one way you could do that is try to put that in the objective function of the principal, but that's not a problem that we know how to solve. If we were to put the part of the payoff of the agent that doesn't depend on the cost of falsification, but only depends on the probability that they're getting the good, that we could solve by it would just change basically the threshold, the desired threshold of allocation for the principal. So that part we could handle, but putting the cost as well, we don't know how to handle. All right. So this is saying, instead of this approach, by looking at the falsification proof optimal, you sort of find a test that strikes a balance between the cost of cheating consideration for the agent and really doing the full optimality for the principal. Okay. Still time for one last thing? Okay. So let me skip that. This is just making the point a bit more formally of mechanism design versus information design. But let me, through an example, let me go back actually to the initial setup where we had groups and resource constraint. This is an example without a quota constraint, but this is trying to illustrate the kind of feedback effect that you may have. So here, I'm starting from a situation where I have two groups that both have a uniform distribution on -1, 1, and I'm going to change gaining ability in one of the groups to see how it affects both groups. All right. So yeah, the groups are equally sized. Okay. They have the same value, the same highest value for the good in both groups, and initially they have the same gaining ability, but I'm going to increase the gaining ability of group 2. Okay, so initially the blue curve here is the optimal allocation, and I'm in the situation where I have very few objects to allocate. Okay, so I'm going to be in this situation where, because I'm in a low priority group, I will not want to allocate to very weak agents, but that means in order to be sure that I don't allocate to these agents, I have to lower the probability of allocating to the top agent. So this probability here is less than 1. Okay, so that's the initial situation, and both groups are getting the same allocation rule because they are completely identical in the beginning. Now I'm increasing the gaining ability of group 2. If I were to keep the threshold, that wouldn't change anything for group 1. Okay, without changing the threshold, they would get the same allocation rule, but it would change for group 2. And the way it would change is, since the stakes are becoming higher, you would get to a curve that looks like this. It would increase everywhere. Okay, but of course, by doing that, I'm allocating the good more often overall, which means that's going to feed back in the sense that I'm going to change the threshold so that I'm back to satisfying the resource constraint. So that would have changed like this for group 2. Sorry, actually, that would have changed like this for group 2. And basically, I have to give more often, so I'm going to lower the thresholds on both groups. So the fact that I increase the gaining ability in group 2 has a positive effect on group 1 and an ambiguous effect on group 2. So that's the kind of feedback effect.
Eduardo,
yeah.
maybe it's time to wrap up.
I'm done.
Okay, good. Okay, so thank you very much, Eduardo, for this nice talk. So now we're gonna open the floor for questions. Okay, so maybe we can start with the panelists. Maybe they have other questions in their minds or any final comments. So I don't know, Julien, maybe you want to start, or do you have something else to add, or any other question, final comment?
I already asked mine during the presentation, the main ones, and I mean, I just want to say that this is a great, opportunity to close the gap between mechanism design and matching and push toward more new techniques for the field. So I like the paper a lot.
So
I'll jump in.
James?
Yeah, thank you.
Yes.
First of all, fantastic paper and fantastic talk. I want to go back to your. First of all, I love the question itself. But I'm going to go back to the motivation you gave for looking at taking the fraud proofness constraint as a sort of the primitive question here, the primary question here. I think you asked about, you mentioned in one of your motivating slides, one reason to restrict attention to the question of insisting on 100% fraud proofness was that you could ultimately say something about how this would compare to the optimal, let me say, fraudulent mechanism. So you mentioned that it's possible that, in fact, likely that the planner might prefer to allow a little bit of fraud, and that might increase welfare overall. So, given the results you have, do you think you can say anything about when, like under what conditions on the primitives would it be? Would the optimal fraud proof mechanism be at least close to the optimal universal mechanism, fraudulent mechanism? Do you have anything to say about like whether there's differences between the groups, what you have to know about the prior on the distribution of types, et cetera, et cetera?
I mean, so the only case where I can really compare is when I have homogeneity in terms of gaining ability and value, and upward increasing difference cost. Then I could do this comparison. Okay, let's put it this way. So I can compute the value and tell you what parameters matter. It doesn't give anything very satisfying, so maybe it's easier to be more qualitative. So let's say that if the stakes are very big, for example, I can get to first best in the unconstrained optimal, right? The reason is that I'm basically increasing the threshold that I'm asking people to satisfy. And if the cost function is very steep, so basically the stakes are high, then I can get the only people to falsify to be the ones that are actually between my true thresholds and the mean threshold that I set up. So in this case, I get first bet.
So maybe like an intuition for that might, and maybe I'm wrong, would it be, so when the stakes are high kind of means you're not going to prevent fraud anyway. And so in your mechanism, one trivial way to prevent fraud is to basically say everybody gets the same reward. So in that case, then all the agents are going to choose their optimal, their best S without worrying about fraud, because changing their S changing their action doesn't change their reward. And then if you also thought what would the optimal be ignoring fraud, you'd also say, look, there's nothing I can do. If I make any differences between the allocation probabilities, I'm doing more to distort the actions that agents are taking rather than improving allocation itself, because I can't prevent fraud. So is that kind of the intuition why when stakes are high, it almost doesn't matter what you basically just have to give up and say, it's just use uniform lottery. Everybody gets a reward and you can do whatever you want. Is that kind of the intuition?
So first I misspoke when stakes are low for the agent, that the cost function is actually very steep. So it's when the cost, it's when it's very costly to falsify that you can get first place.
I see. I think it's on both. So when it's very costly to manipulate, then it's there's no fraud problem to begin with. You can do whatever you want. At the other end of the spectrum, when fraud is almost costless, it's like there's nothing you can do to prevent it. So you're going to have to use if you wanted to prevent it, you'd have to use a uniform lottery to just give away, to basically ignore the signal. That's the end I'm on.
Yeah, when agents can falsify easily, you have to use this lottery to prevent fraud.
May I jump in for a moment, because I think I see what James is.
Yeah, go ahead.
So in the cases where we have zero cost, there is no difference in either case, as you said, because in both cases we cannot do anything. In cases where there are high costs, at the optimal test, which is not falsification proof, you might have some good states be assigned objects because they falsify to a higher state, and you basically leverage falsification by states that you want to assign objects. So you never really get the first best, because the optimum involves like high falsification costs, which are borne by the agents. So in a sense, there is really no comparison unless we write down a grand objective function that includes the welfare of agents. And in that case, actually, those tests that we are deriving here could be truly optimal. Is that helping at all?
Yeah, I think that clarifies. Thank you.
So thank you. Any question from the audience? I mean, I have a little comment question, okay, and it's more asking for a wrap up rather than a question. So, I mean, to me, the thing that has called my attention the most, is how you can go beyond the analysis of the first order approach and provide a full characterization of the optimal mechanism in this setting. But what I didn't get it, I think it is hidden in this definition of how do you call it, universal increasing differences, or universal decreasing differences, pardon?
Mm-hmm. Yeah.
So, I mean, yes, my question is that, do you have a clear-cut, as far as I understood, you have a clear-cut distinction between under which assumptions the first order approach is going to hold, under which assumptions the first order approach is not going to hold, okay? I think that you had that result. So my question is that, can you just repeat these two cases for us and perhaps refer to some real examples so that we can get an understanding of what is the kind of situations in which the first order approach may fail, no? And then the optimal non-fraud mechanism is actually a non-trivial one, a complicated one, no?
Yeah, so essentially it has to do with the returns to scale the returns on the scale of falsifications. That's sort of the interpretation that we can give. Essentially, if the more you falsify, the less the more the marginal cost decreases, right? which is the upward increasing difference assumption. So concave cost function in the amount of falsification, basically. So it becomes sort of less marginally cost if you falsify further. So if you've already hidden some of your income from the tax authorities, hiding a little bit more is not as costly as it was to hide the first unit. So
I see.
If that is the case, then we cannot do first order, because typically the importance incentive constraint that we want to satisfy are going to die far away.
So maybe related on this, so I understand that, I mean, if you have decreasing returns to scale, then obviously you want to go to manipulate far away, and then first order does not apply. What's striking me in your optimal transport problem is that the threshold at which you separate the two depends, if I understand well, depends on the W and not the C itself. And it's exactly aligned between the objective of the policymaker and the types that will. So that was surprising to me, at least, that this threshold S hat, if I'm not mistaken, is coming from the W, not from the cost itself. I mean, the fact that the first order approach does not apply is, I kind of get it when you have decreasing return to scale. But it's surprising to me that it matches exactly this S hat, and that these two things binds nicely together to then end up at an optimal control. So do you have an intuition of exactly why it's working exactly at that threshold well? Or,
I mean, it's a bit lucky that we recover, in a sense, the optimal transport problem, but the way we're doing it is by sort of changing the unit in which we're measuring things. Initially, we're thinking of it as, think of scores as being locations, and think of cheating as transporting scores from a certain location to another location. Okay? And not scores, actually, it's transporting agents, because that's what you're dealing with initially. You're dealing with masses of agents that are at the different scores. Okay? So think of the aggregate cheating as transporting these masses of agents from certain scores to other scores. The optimal transport analogy is done by sort of, instead of measuring things in terms of masses of agents, we're going to measure them instead in terms of masses of social surplus.
This I understand, but the fact that, so when you relax your IC constraints, it's really the one that are below S hat, if I understand well, that would like to misreport above S hat. Am I missing? Is this intuition, or is it different?
Yeah, this will actually the way we're doing. We're just getting rid of the orders from the program. I mean, it's basically, it's a way to find out that these are the ones that matter. But we just start by taking them out. Then we find the optimal test under this relaxed problem, and we verify on the shape of the test that we obtain that indeed these are the only incentive that the others are going to be satisfied by the optimal test. What I said at this moment is that, again, the returns to scale assumption was important for that recovery.
Okay, so sorry to interrupt. Just to keep with the schedule. So I think it's probably now time that we finish what is the more formal part of the seminar. We stop the recording. So we thank everybody for joining us today. And please, remain connected, and we can continue, with a more perhaps informal discussion. Okay, so